Hi, everybody. Thanks, Brad, for the introduction. So I'm Piyush, and I'm a PhD student at the Australian National University. And today I'll talk to you a bit from the modeling side of star formation and what we have been doing up so far, in particular on the effects of magnetic fields and how they can influence the initial mass function of the first stars. So let me see if I have the cursor to operate the slides. Yep, great. Okay. Um, So the reason why we care a bit about primordial magnetic fields when we talk about star formation, in particular population 3 star formation, is because there is very little doubt now that a primordial field existed in the early universe. Although the field strength is largely unconstrained, as you can see from these numbers that I've picked up from a couple of reviews, um, people do believe, and there are very strong theoretical arguments going back all the way from particle physics to cosmology that tell us that there was some non-zero weak seed field that existed in the early universe. And in fact, it is also believed that a fraction of the magnetic fields we see in galaxies today came or was primordial in origin. So the question that we're trying to understand is, let's say we have some non-zero weak field in the early universe. We would like to know how would they impact population 3 star formation. Before I go on to the next slide, the reason from the star formation point of view, the reason population 3 stars are different than stars, for example, in the Milky Way, is because the molecular clouds collapse on a completely different pathway uh, when you talk about first stars as compared to current day Milky Way stars. And this completely different pathway is mainly guided by the absence of dust and metals. So star formation in the primordial universe is a very, very different problem than star formation in the current day universe. And this is one of the reasons why the effects of magnetic fields or radiation feedback, for example, haven't been explored a lot when we talk about population 3 star formation. So to do this, we have conducted a suite of 3D MHD simulations using the code Flash, where we have a bunch of initial conditions that we get from cosmological simulations. And the main thing to note here is that we then vary the field strength depending on what we feel or what we find would be appropriate if you take, for example, the magnetic field amplification into account on cloud scales. So we saw that the field strength is very, very unconstrained on megaparsec or cosmic scales, but we are more interested in knowing the field strengths at the cloud scales, which can vary from anywhere between 10 to the power minus 15 Gauss or 1 femtogauss to a very strong field, which corresponds to 10 to the power minus 6 Gauss. And these are the two main cases that I will be talking about today. So before we go on to talk about how these fields can influence star formation, we'll have a quick look at how these fields change themselves during the formation process of population 3 stars. So on the left side, in the first and the second plot, the y-axis tells us how the field is amplified and then what is the saturation level of magnetic field. The red colored bands are for the weak magnetic field cases and the blue ones are for the strong magnetic field cases. So the takeaway from this plot is that given sufficient resolution in the simulations, even the weak field runs or even the weak magnetic fields are amplified to near saturation values, which is seen from the bottom panel in this figure. So what that means is no matter how weak a field is, uh, during the formation of these stars, because of amplification of the field on exponential levels, the field can grow up and be saturated very quickly. So we should be expecting dynamically strong magnetic fields when we talk about population 3 star formation. Given that these fields or even initially weak fields can be amplified to strong field values, we can now understand or now look into how can the affect the population 3 IMF. So This is just a particular example of a simulation which has only the magnetic field strength that differs. The top panel shows the projections in the three directions of densities, and these white little dots that you see on the screen are the different stars that are forming in the simulation. And you can see by the time we stop our simulations, there are already 7 stars that have formed from one primordial cloud when you do not have any magnetic fields. Whereas if you do have a magnetic field, you can see that only 1 star forms for the entirety of the simulation. So this example kind of tells us that magnetic fields can really suppress fragmentation in primordial clouds, and that can lead to a suppression of the formation of more stars, in particular low mass first stars. And to quantify this, here is a zinc mass distribution, which is basically a mass distribution of the stars we form in the simulations. And I've only shown 2 cases here, one with the zero field, the pure HD case, and the one with the strong field. And you can immediately see from the PDF that the low mass end of the first star distribution is highly suppressed when you have magnetic fields in the simulations, given you, if you have sufficient resolution. And if you were to do a simple Kolmogorov-Smirnov test to figure out whether these 2 distributions are in fact different, you get p-values of the order of 10 to the power minus 5 to 10 to the power minus 3, which basically means that there is like 1 in a million or 1 in 1,000 chance that you will get the same IMF if you have magnetic fields versus if you don't have magnetic fields. So to summarize, I don't remember I had this slide here. This slide just basically, it's more for the numericists, and it talks about how you have to be cautious in terms of analyzing these statistics, because if you don't have sufficient number of simulations to create this PDF over, you might end up getting wrong results. Just to summarize, dynamically strong magnetic fields were likely present during the formation of the first stars, because even weak fields are being amplified to very strong field values. So that means that magnetic fields can suppress fragmentation in primordial clouds, and they then significantly affect the population 3 IMF. In particular, they make it top heavy because they're suppressing the formation of low mass stars. And perhaps the last point here in the summary is a very important and interesting point, which is when we compare this scenario to population 1 star formation or star formation in the Milky Way, we find that magnetic fields have a subdominant role as compared to other processes like radiation feedback, which set the initial mass function. But we argue that this might not be the case for population 3 stars, because radiation feedback is weak, but also it starts very later on. It only acts for very, very high mass stars because of the absence of dust, which means that there is a larger role for magnetic fields to play in setting the population 3 IMF. And there are the details of all of this works are in a couple of papers. One of them is already on archive, and the other one will be on archive soon as well. So thank you very much for listening, and I'm happy to take any questions.
Thank you, Piyush. All right, we have one question there. Are you able to see that, Piyush? You can answer that one live if you choose to.
Right, okay. So the question is, are the magnetic fields of population 3 stars something we can test observationally? It's a very interesting question. People have tried to do that, but the only observational constraints we get are on galactic scales or higher. So basically scales more than a few kiloparsecs, all the way ranging to megaparsecs. But there has been some recent progress from people who study dwarf galaxies, because it is believed that if a dwarf galaxy had a primordial magnetic field, it will not have been affected much because of low star formation activity and feedback. So we do have some sort of constraints which range from 10 to the power minus 9, so 1 nanogauss to 1 femtogauss. But these are on galactic scales or larger scales. So on cloud scales, I think it is still going to be tricky to get to the point where we can really do this.